In this, the second part of our exploration of optimization, we'll have a look at a few mechanisms or techniques or approaches we can use to improve the performance of the code that we write. So, as mentioned in the previous talk, there's lots of different ways you can think about optimization, from the design down to how we actually code and implement it. Big decisions are ones that are made at the design level, and as mentioned, they are the ones we need to get right first of all. They, generally speaking, have the greatest overall impact. But alongside that, if we have a good, efficient design, good choice of algorithms, stuff like this, then how we actually code it can have quite a significant effect as well in terms of how it performs or the speed of it. So in this one here, we're going to be down at the level of coding and look at a few different techniques or approaches or things we can try to spot and then to remove that should hopefully speed up the overall execution cost. But when I get across, most important bit is that this is tinkering, this is tweaking. If you want to have fast, efficient code, then you do that and you get it mostly right through the design of it, not through tweaking code, but nonetheless, we're looking at adding those little refinements onto it. In terms of the code that we get to be executed, there's a useful guideline to keep in mind, known as the different names like the Pareto effect, the 80-20 rule, stuff like this. And generally speaking, what the 80-20 rule says is that roughly, if you apply it to execution of code, 80% of the CPU time is going to be spent in 20% of the functions or the methods. Now, the exact percentages are irrelevant. It's unlikely to be 80 and 20. That doesn't matter. What does matter is that the majority of time, execution time, is very likely to be spent in a small number or minority of methods. And that ties into the whole notion then of what's known as the common path, how you typically flow through code 9 times out of 10. Also gets into the notion then that there can be bottlenecks. There can be certain areas within your program where you're spending most of your time, where small tweaks to this can actually have quite a significant overall return in terms of the speed of the program. Now, because that is the case for the vast majority of different programs, if we want to optimize the code, an utterly essential tool to use is a profiler. So you can run a profiler, it'll and then just go through your program as per normal. It'll look at it, it'll time it'll have a measurement of where time is spent, it'll count the number of times you call methods, and I'll give you quite a detailed report at the end then that you can actually delve into to work out where most of the time is being spent. And that's where you then focus your optimizations, because you'll get most return then. You don't want to be having to optimize 100% of your code base. If you can optimize only 20% of it and has a very significant impact, that's great. Some of the things then that if we identify a method where we're spending a lot of time and we want to try to speed it up, some of the things that we can look for to see, well, are we doing this? Is this an opportunity to improve it? We'll go on to these now. We'll start off first of all with redundant computations and the whole notion of caching. So redundant computations, as you might expect, are unnecessary computations. They're ones that quite often are repeated. I've got a couple of examples on this slide. At the code fragment at the top, we've got a for loop, doing it 100 times. Inside the for loop in line 2, we're calculating m times n. So m is some constant, n is again some other value. So it doesn't change, it's independent of I, the iteration variable for that particular loop. Now, because we're calculating that every single time, that is a redundant computation. If we did it once and remembered it, then we could make use of that value within the for loop. Now, that's good. We could do it. We could put it outside. If we were to put it outside as a programmer, it would look a little bit more ugly in terms of the ease of understanding what the code is doing, but run a bit faster. Now, the good thing here is any decent optimizing compiler will be able to detect that and will be able to do that on your behalf. So you don't have to pollute the code base to get that improvement. The example shown on the bottom is a little, well, it is more problematic. So the one at the bottom, again, we have a for loop. It's functionally the same as one at the top, but just a little bit more obscure. In line 2, we're calculating the result of something, and we're calling some function to do that. And into that function, we're passing in some arguments. And the second argument in this case is the return from another function. That just happens to be a function that will return a fixed value. So we, as programmers, because we presumably understand what these functions do, we might know that that function will always return the same value within the context of that for loop. So there, it should be the type of thing you get once and then to reuse, not to constantly call the method. It may not be possible for the compiler to be able to work that out, that function will always return a fixed value, so it then can move it outside. So there may be some cases where if you think that, well, the compiler may not detect this, you can test it, I suppose, the easiest way. You'd have to do it manually ourselves. So there are both examples here of computing something multiple times, where you just need to compute it one time and then to remember what you have computed. This notion of getting something or of calculating something, holding on to it, the general form of this is known as caching. You store data that is frequently accessed, or you believe likely then to be accessed in the very near future. And ideally you store it in a location that is more convenient to get access to. And it's a very common technique that if you're trying to optimize your program for speed, then caching, remembering data, putting it close to where it's notionally going to, or making it easy to get access to, is a very common way of improving the execution speed. The cost of this is that we need to use more memory, but that's mean there's a trade-off between executing for or optimizing for CPU instructions versus memory footprint. The actual image we have here is one of CPU, and they'll use the same notion for both instructions and for data, that you will have a number of caches at different levels. So generally the level 1 caches, or you have some cache actually on the die of the CPU itself, they're going to be really, really fast. More expensive to create that types of memory, which means you can't have a large size for it. And then the very small amount up to maybe a level 1, level 2, level 3 cache, where you're having greater amounts of memory, slightly slower, and then eventually reaching out to main memory. The instructions and the data that you're accessing will filter through those caches, so they're always, or the hope is that the instructions you need and the data you need will always be conveniently accessible to the CPU. You can get them quickly. Some other examples then of caching where it can be very useful to do this. So over on the left hand side we have the notion of disk access. Even with solid state disks, getting data from them is very slow compared to the speed at which a CPU waits. So you will have many cycles potentially being lost if you're sitting waiting for data to come in from a solid state drive or across a network or some type of connection there. So example here, where possible, only open and read a file once. You don't want to be constantly going back to it to try to read in a chunk at a time. Read it all in once, cache the results. Again, you've got to store all this in memory and make use of them. So that is going to be faster than going back to it repeatedly and pulling in bits, but at the cost of additional memory. Mathematical operations. So quite often here, we're not writing these operations, we're making use of them within a library. Some of the mathematical operations are deceptively complex. They can occupy a lot of CPU cycles. One of them is to the power, x to the power of y, sort of the generic form. Very expensive operation. So if you, I suppose you have to sort of get to know which ones are going to take a lot of time and effort, but if you're using those within a loop and in any way there's opportunity to cache it, that most certainly should be done. It will give you a significant return. Object allocation is another one. So if we have a method that we're calling repeatedly or often, it's on the common path, then we need to be careful, because the cost of actually creating a new object and getting rid of it, that could dwarf the actual cost of doing whatever the object's meant to do. So in this sense, we may want to have a pre-created object that we just simply tweak some of the values of and then reuse. We never really get rid of. Ditto over the right hand side for threading as well. If we have worker threads that are fired off to do a bit of work, there's a cost involved in actually creating and setting up a thread and pulling the thing down. And that cost, if the thread doesn't do much work, that cost can actually, again, be more than the cost of the work that's involved. So it can, in some instances, be useful to have a pool of worker threads that you can always keep active and just give them out activities for them to pick up on. If you're thinking about caching, so this is the notion of you are sort of calculating or storing something other than the original location in which it exists. You have to then at least ask the question and to think about it, is there any notion of invalidation here, that if the data that I am caching, does it have a lifespan? Can it go out of date? Is it likely to change based on the original source location, so that the value you have in your cache is now an out of date and old, a different value? Now, in a lot of cases, that won't be the case, because you will be reasonably confident that yes, it will be maintained. But in some cases, it can be different. So if you're reading in from a file, or you have a network connection, you pulled in some information, the file, the data that you're pulling across from the network, from the source, it might be changing independent of your program. And that may or may not be an issue, depending on what the program does. But at least ponder and ask, for me, for this particular piece of data, do I need to be concerned about the accuracy, the timeliness of the data? There's two common approaches, you can see it down here, that are used where there is a need to handle this. So the first one's use a callback mechanism to notify the cache of a data change. So whenever there is a change to the data, there's a mechanism that will call it back, and it will then give you an opportunity to push the new value into the cache. The second one is to have a lifetime value, so that when you add a data value into the cache, you say that it will have currency for half an hour or returns whatever it is. After that time, you push it out of the cache and you re-get it in or update or populate the cache again. Pre-computation then is similar to caching, except the notion here is that we do it before we actually execute the program. So it could be something that's done at compile time, or as part of some other process where we generate the data and we store the data. Often used, for example, within games for things like pre-backing light information or other related stuff. Not a new idea. The actual image you have on this screen is from an old logbook. So back in ye olden days, before calculators were anywhere common, or smartphones with your calculator on it, you had a book with tables full of logarithms and the calculated values. So there they were pre-computed values that were then shared out and could be used. Next up is lazy evaluation. So this comes into how we evaluate or make use of variables. So lazy evaluation entails that you defer computations until you actually need them. And on the surface of it, that makes good sense. So you can see an example over here if we have a look at the code. We've got a method called sendMessage. It takes in some string that we're going to try to send. Because we're sending it, we're assuming that, well, most of the time it's going to work. Some of the time there could be an error, we weren't able to send it. So in line 3, we're declaring an error message, and that's what we'll use if there was any problems with sending it. We'll use that error message to report the error out. Line 6, we've got our try send message, and we're then switching the return from that. So it's going to send something and give us back a message. And you see the comment in line 5 that most of the time it's going to be sent without any trouble. Line 8 and line 10, the two case statements are ones where we have a problematic return from it. So in this case, connection not established or message rejected or whatever the thing's going to be. But at that point, inside those cases, we populate our error message and we then log the thing out. Line 15, we're finished. Now, as it is written at the minute, this is a little bit inefficient because in line 3, we always create a string. It's automatic variables created on the stack, but it's always created. And at line 15, it's always then destructed and removed. So it'll involve allocation memory quick to do in the stack. It'll involve calling the constructor, a little bit of setup. It'll involve calling the destructor, a little bit of breakdown of it. But because 99% of the time or whatever it is, we don't actually use this. This is just wasted computation. It would be better to do what we do down at the bottom here, which is only when you know that you need to send, in this case, an error message, do you create the string associated with that error message. So the cost is only incurred when actually it needs to be incurred. So that's again something to look out for, useful thing to bear in mind. Related to that, you see a few more examples here about object construction. So where possible, object creation should be deferred until all the elements needed to construct the class have been obtained. And it depends upon the exact form of construction, whether or not that is an important element. The example at the top gives you an illustration of where it is an important element. So in line 3, we're creating, we want to have a string called m. So we create it there, the default constructor will be called. In line 5, we're actually taking together, or bringing together the information we want to populate within, in this case, the string. In line 7, we're using the copy constructor then to transfer that across. So we get an implicit conversion and assignment to it. So the top example, we are doing unnecessary work. We're creating something, we're getting some data, and then we're basically repopulating the object with that data. One at the bottom is a better example. So there we get the data that we need, and we then construct the class immediately using that data. So it's just a little bit faster. These are not major things, but if you're calling that frequently, then all of those little bits can add up. Useless computation. So useless computation is computation that has no purpose. It's different than, for example, lazy computation or the other ones. If you find anything that is useless, it's not actually necessary, it doesn't add anything to it, it simply should be gotten rid of. It's of no use whatsoever. It is useless. Okay, next thing we want to have a look at is the notion of evaluation order. So this gets into how we deal with things like if statements where we have some logical condition that we need to evaluate. As a reminder, you can see them down here at the bottom. The first one we have if condition 1 or condition 2, so E1 or E2. So if E1 evaluates to true and it's an OR statement, then we stop execution at that point. We don't worry about evaluating E2, because if E1 is true, then the whole condition is going to be true because it's an OR statement included in it. So if E1 evaluates to false, only in that case will we evaluate E2. So this gives us opportunities here in terms of how do we structure things so that we don't need to evaluate E2 as often as we can. So we just mostly wanted to trigger an E1. If we have the other bit, the if E1 and E2, in this case, if E1 evaluates to false, then evaluation stops. We don't consider E2, it's automatically false. So there it's the other way around, but we have an opportunity here in terms of how we structure these things to potentially avoid needing to evaluate E2. And that'll save us a bit of time and effort. As to the sequences of doing these, they're fairly straightforward. So we look at the if first of all. So if E1 or E2. So if E1, E2, if they're equally likely to be true. So in doing this here, we're thinking about the conditions. We're thinking about what's the probability that this condition could be true. And we're thinking about the cost of evaluating that condition. How easy is it to evaluate that? Now, if it's a Boolean variable, that's just a memory lookup. If it's a function you have to recall that returns a true or a false, then it's the cost of executing that function and whatever it does inside it. Now, if they're equally likely to be true, so we think about both of our conditions and we go, probably, it's much the same in terms of their probability to be true, then we pick the one with the lowest, what we perceive to be the lowest computational cost, and it goes first in the evaluation order. Conversely, if E1 and E2 are of equal computational cost, so they're equally as quick to calculate, then pick the one that you think is most likely to be true and put that first. And that will ensure then, for at least for this coupling, that we've got the most efficient setup. And it scales up to A or B or C or D. You can do the same process with it. If E1 and E2, so in this case, if we're thinking about the two conditions, and they're equally likely to be false, because false is the desirable condition here in terms of getting an early out in their evaluation. So if they're equally likely to be false, then the one with the smallest computational cost we put first. and if they are of equal computational cost, then the one that is most likely to be false, the thing that will break us out of the evaluation, we put that first of all in our AND statement. And again, this scales up to A and B and C and D, so you can rearrange things in a way so you try to optimize or to have the quickest evaluation of that overall expression. Key takeaways in this, I mean, we've only looked at a small number of different coding optimizations that we could use. There's I was going to say an endless number. It's not an endless number, but there are many, many different optimizations you can put in. This has just been a flavoring of some of the more common ones. And it's worthwhile sort of delving into a good book on optimization by way of finding out about a lot of the other ones. So general takeaways from this, do you need the results now? If you don't, defer calculating stuff or constructing objects until you actually need it. Do you know the results already? So it's something you've worked out. So if something you computed earlier, consider if it's worthwhile caching and storing and making that available for reuse. And again, there's a cost-benefit analysis. Do think about the flow of execution through your program. Which way is it likely to go through? And use a profiler to actually determine this accurately. And you're then trying to optimize that flow. And that can get into fine things like your logical conditions, your ifs and your ands and your ors, and structuring them in a way that you try to optimize flow through the program. So a few illustrations. As mentioned, there are many, many other ones. So I would encourage you to delve into those to have a look at them, because they're useful things by way of enriching your overall programming knowledge.